All right, diving a little deeper, we are into multiple regression full on. So here we go. Assumptions. You are familiar with this particular equation, or at least a version of it. All you will notice here is at the end of the equation there is a plus epsilon. Epsilon accounts for the errors between what we expect, what we can calculate, and what we actually see. So epsilon accounts for the errors. You won't ever have to put numbers in there or anything like that. This is just a way of writing the equation that accounts for the error factor. So the assumptions of this particular multiple regression equation are, there are three of them. The first is called the independence assumption. And that is that the error disturbances, epsilon, are independent from each other. For instance, if one point is above the trend or above the line, say the trend line that you impose upon the data points, if one point is above the trend, this does not make it more or less likely that the next point or another point will be above the trend. Each one of the points is independent of all the other points with respect to their distance from the trend line. Next, the variance assumption that the underlying error disturbance epsilon has the same standard deviation. It doesn't get bigger, it doesn't get smaller as x increases, x of 1, x of 2, all the way up to x of p. So if you begin to see something in the error, if you graph the errors and you saw something that looked like a trumpet getting bigger and bigger and bigger, you would say, whoop, that's the variance assumption. Or if it looked like a funnel getting smaller and smaller and smaller, as x increased, you would say the underlying error disturbance epsilon does not have the same standard deviation. So the variances need to be independent of each other, and they can't get bigger or smaller. And lastly, there's a normality assumption, and that is that the error disturbances, epsilon, has a normal distribution. That is, if you remember your earlier calculations from chapter 1, in a normal distribution, 68% of the observations are plus or minus 1 standard deviation, and 95 are plus or minus 2 standard deviations, and almost all of them are plus or minus 3 standard deviations. So here we would say errors will seldom be outside the range of from minus 3 sigma to plus 3 sigma. You won't get errors outside of that if the errors are normally distributed. So these are the three assumptions that have to hold for us to be able to use multiple regression. All right, so here is the regression model that we're going to be using. That the output variable y is equal to some intercept, b, plus the first slope times the value of the first variable, plus the second slope times the value of the second variable, etc. All right, so to start with, we need data on how the output y has been related to the inputs in previous cases. So that means you need data to start with, and data from past observations or a survey or something like that, so that you can come up with what are the m's, what is the b, and what are the slopes that need to be used to predict what y will be in a given situation. So we describe the pattern of observed dependence with a multilinear rule. We're assuming that all of the relationships between the variables and the output are linear. There's no logs going in here. There's no exponential functions or anything like that. So all we have to do is come up with values for the unknown parameters, the intercept b, and all of the slopes for all of the different variables in the problem. Now there's a thing called the sum of the squared errors. Sum of the squared errors. I wish I could draw this for you. Imagine you had, let's just go back to a simple case, and this is going to be a mental experiment. A simple case of one x variable and one y variable. And you draw some scatter plot. You come up with a scatter plot with the x's and the y's, and you see that they look kind of like an oblong cloud. And you ask Excel to draw a trend line through them, and it draws a line through somewhere through the center of the cloud. You can then calculate the distance between the line and each one of the points. Those are called the errors. They're also called the residuals. All right, so you've got a bunch of lines, some that point up to the point and some that go down to the point. Well, if you turn each one of those lines into a square, in other words, if it's 1 unit long, you make it 1 unit long and 1 unit wide, and you make it a square. So what you're doing is you're squaring the errors. And these errors squared actually are a bunch of areas. So then you sum up the areas of all of the errors squared, and you get the sum of the squared errors, the SSE. And lastly, we know that the predicted standard deviation of the standard error there is the square root of the sum of the squared errors over n, the number of observations, minus p, the number of variables, minus 1. All right, you may not have to use these ever manually in any of the problems. You just have to be aware of them so that when Excel calculates them, you know what they are. So let's go to our Washington, D.C. apartments example. And we came up with the idea that the sale price could be predicted from the slope of the, so B, some base value, plus the slope of area times the actual area, plus the slope of beds times the actual number of beds. All right. Here is the data. Column A, we don't have to bother with at all because it's just an index number. Column B is the area, so that's, and we're going to be calculating the relationship between the area and the price. So that'll be the slope of area with respect to price. And the last one is the number of beds or bedrooms times the relationship between the number of bedrooms and price. And here we have the sales price, D, and that's what goes over here to the left of the equal sign. That is our sales price. And we have a bunch of these. I think we had 108 of them. No, we got 150, I can see right there from the observations. All right, so this is a picture of the output of Excel in creating I think I should probably demonstrate this for you, so hang on just one second. So here is an image of the data itself. I've removed the column that dealt with the valuation of Jim, for that's a later discussion. So all we have is area, beds, and price. Now to actually do this multiple regression, here's what you do. You select all of the data. Actually, no, we don't need to select it beforehand. You just need to come in here to data, and I don't have it. Excellent, perfect time to demonstrate. All right, so if you click on the data and you do not see the tools over here that say data analysis, then you need to do the following. I'm on a PC right now, so you would go to File, you would go to Options, then you would go to Add-ins right here. Click on Add-ins and go to Excel Add-ins Go down at the bottom. and you would put a check mark next to the analysis tool pack, and I would also recommend the solver. We're going to use that later too. And then click OK, and watch what happens up here. So I get another submenu called Analysis and something called Data Analysis. Now, if you're on a Macintosh, there is a menu item called Tools, and you just click on Tools and scroll down to Add-ins, and you can select the Data Analysis pack and the solver that way using a similar thing. So now we've got data analysis. These are like statistical steroids for your copy of Excel. They are available on all copies of Excel. They're just not active until you put those little check boxes next to them. So let's click on Data Analysis. And here is the dialog box. The one that we want is called Regression. So we scroll down until we get something called Regression. There it is. Click OK, and you get the dialog box for Regression. Input Y range. What is the Y is the output variable here, and in this case it's going to be price. So I click on this little box right here. Click on the word price, that's the label. Hold down Shift, Control, and the down arrow, and it will select all the data to the bottom of you notice it goes all the way to the end of the data. And that's from D1 to D151, and that's correct. So I can hit Enter, and I'm back in the dialog box. Now the input X range, if I click that box, I've got two inputs. So I click on the word area, Shift right arrow once, Shift Control down arrow to go to all the way to the bottom, which was 150 observations, and then hit Enter. So from B1 to C151 are my inputs, and my output is from D1 to D151. Now, did I did not select the labels? And the answer is yes, I did. And it's important that you do that. If you don't do that, you're just going to get an output that says variable 1, variable 2, etc. But since I did select the actual area, beds, and price words, the labels, I want to be sure and click on the little box that says labels. Now for this particular problem, the only thing else I'm going to change is the output range because I want it on this same page. So I want it to be here. Click in the box and say put it in G1. Click OK. And there is the fancy output that comes from the regression routine. Double click on the border between any two and it spreads it out to the... Now there's other ways to clean it up here to make it a lot easier to read. I first take these on the home screen and decrease the precision because, heck, these are estimates anyway, and so I don't need 9 decimals of precision. I turn this, which is 1.56 times 10 to the minus 28. I go up here and turn that into a number, and you'll find that that's essentially 0. And even if you increase the precision, it's still 0. So that's Excel's way of saying 0. All of these don't need to be that precise, so I would select them and decrease the precision down to no more than 3. All right, so this would be what the output looks like, and then you can select them all and double click on the border and it shrinks it up. So now it's nice and clean and I can read it and those kind of things. So let's go back over to the PowerPoint. So here is the output of that from the PowerPoint, and we see that the R-squared value is 0.57. Well, there were 150 observations. The standard error is 9.5 of this model. So on average, we can be off by $9,534 in estimating the sale price. These variables, the area and bed number of bedrooms, account for 57% of the variation in price. And we can come down here and say, okay, let's Let's see what the coefficients are. Well, if we were to put in something for B, it's the coefficient right here by the intercept. So 49.095 would be the coefficient for B. The coefficient for the slope of area would be 4.8, so $4,813 per 100 square feet. And then the number of bedrooms turns out to be a minus $178 for an extra bedroom. So now we need to interpret that. So we look at the coefficients to be able to make the equation. And we say each extra 100 square feet adds $4,813 to the price. So the value of space is $48 per square foot. Fairly similar to what we got in the naive plot of price against area. However, in the naive plot of number of bedrooms against price, we got that each bedroom was worth $10,000, but that's not true. Each extra bedroom subtracts $178 from the price. Very different from that number we got from the naive plot of price against bedroom. So this number 49,095 is not really meaningful, as it formally values an apartment with 0 area and 0 bedrooms, non-existent. It is best thought of as a baseline figure to which we add or subtract amounts depending on the number of bedrooms and floor area. Now, the next thing that's important in this output down at the bottom are the t-values and p-values, the t-statistics and the p-values, which are right here in the center. All right, let's start with the effect of any one of the inputs. So let's talk about area, for example. What is the effect of the input area measured by the slope parameter, m? So what is the effect of this slope right here? When this parameter equals 0, the input has no effect, obviously. But knowing which variables matter, which ones have an effect and which do not, is one of the aims of this particular regression procedure. All right, so the t-value measures the size of the observed effect in statistical units, standard errors. The p-value is the chance of seeing an observed effect as large as the one sees in the data just by sheer chance. So how would we interpret this? The area here gave us a t-statistic very large, 8.6. The probability of seeing a value of 8.6 just by chance, if area didn't matter, is 0. 0, 0, 0, 0, 0. Now, the next one, the number of beds, we got the coefficient of minus 178. The t-statistic is very small. It's almost 0, close to 0. And what's the probability of seeing a value of negative 0.1195 just by chance? And the answer is very high. It's 90%. So 90% we could see a value this size just by chance, which tells me that number of bedrooms doesn't matter. These are how we calculate the t-statistics and the p-values. So the hypothesis that we're going in with is that the slope is 0. In other words, it doesn't matter. And the alternate hypothesis is the slope is not 0. It does matter. If it's 0, it doesn't matter because no matter what the x is, it won't affect the y if the slope is 0. But if the slope is non-zero, then it will affect the y. So we reject this null hypothesis that the slope is 0 and conclude that any one of the x's has an effect if the p-value is smaller than some chosen significance level alpha, which is usually 5%. So we just saw a value of 0.90, which is much bigger than 0.05, 5%. So we would therefore say This P is well above our significance level. Therefore, we would go back to the data and not include bedrooms in our equation to be able to calculate the impact of area on price.